Hello friends, myself I am Arinas Kumar. I am studying in Sri Venkateswara College of Engineering, Chanakya section, Computer Science. And today's my topic is Theory of Computation in Exploring the Power of Deterministic versus Non-Deterministic Finite Automata in Language Recognition. This presentation dives into the fascinating world of the finite automata, exploring the power and limitations of deterministic and non-deterministic variations in recognizing languages. Introduction to finite automata. Deterministic and not non-deterministic. There are 2 points: deterministic finite automata DFA and non-deterministic finite automata NFA. Deterministic finite automata means DFAs are machines that process input symbols one at a time, transitioning to a new state based on the current state and the input symbol. Their behavior is completely determined by the input and current state. And we goes to non-deterministic finite automata NFA. NFAs are similar to DFAs, but they can transition to multiple states simultaneously based on the input symbol. This allows for a more flexible and powerful way of representing languages. Next is deterministic finite automata DFA definition and properties. Formal definition. A DFA is formally defined as a tuple Q, sigma, alpha, Q naught, and F, where Q is the set of states, sigma is the input alpha weight, gamma is the transition function, Q naught is the initial state, and F is the set of accepting states. And properties. DFS are deterministic, meaning that for each state and input symbol, there is only one possible transition. They have a finite number of states and accept regular languages, which can be recognized with a finite amount of memory. Next we goes to non-deterministic finite automata, NFA definition and properties. Formal definition. An NFA is defined as a tuple of same as DFA, Q, sigma, gamma, alpha, Q naught, and F. Similar to DFA, but the transition function alpha can map a state and input symbol to a set of states. This allows for multiple transitions from a single state. Properties. NFAs are non-deterministic, meaning that multiple possible transitions can occur from a state based on the input symbol. They can also accept regular languages, and their acceptance is based on the existence of least one accepting path. Next is comparison of DFA and NFA. Strengths, weakness, and equivalence. Strengths of DFA. DFAs are easier to implement and have a predictable and unambiguous behavior. Unambiguous behavior. Their deterministic nature simplifies analysis and debugging. Strengths of NFA. NFAs are more flexible in representing languages. They can often be simpler to design than DFAs for the same language. They can accept languages that are easier to represent using NFA and DFA. Next we goes to equivalence. Despite their different structures, DFAs and NFAs are equivalent in their ability to recognize languages. This means that for every NFA, there exists an equivalent DFA and vice versa. So next we move on to algorithms for converting between DFA and NFA. NFA to DFA conversion. The subset construction algorithm is used to convert an NFA to DFA. It involves creating a new DFA state for every possible subset of NFA states and defining transitions based on the NFA's transition function. DFA to NFA conversion. The DFA to NFA conversion is relatively straightforward, as a DFA can be considered a special case of an NFA. The conversion process can be done by simply adding a new non-deterministic transition from each state to itself for any input symbol not present in the original DFA's transition functions. Next we goes to applications of DFA and NFA in language recognition. Lexical analysis. DFAs are commonly used in lexical analysis, which is the first phase of a compiler. They recognize keywords, identifiers, and other basic tokens in the source code. Regular expression matching. NFAs provide a flexible way to implement regular expression matching. They can recognize patterns within strings and are used in text editors, search engines, and programming languages. Network security. DFAs and NFAs are used in firewalls and intrusion detection system to identify malicious traffic. They can recognize specific patterns in network packets to detect and block malicious activities. Next we goes to case studies, practical examples and real world implications. Google search. Google search uses DFA and NFA techniques to effectively match search queries with relevant web pages, enabling efficient indexing and retrieval. Network monitoring. Network monitoring tools use DFA and NFA to detect network anomalies and security threats, ensuring smooth network operations and protecting system from malicious attacks. Compiler construction. Compilers utilize DFA and NFA to recognize the syntax of programming languages, enabling the translation of source code into executable programs. Next is last conclusion and future directions. Powerful tools. Deterministic and non-deterministic finite automata offer powerful tools for language recognition. Their ability to represent and analyze patterns is essential for various tasks. Continued research. Continued research explores the limitations and potential extensions of finite automata, investigating new approaches and applications for language recognition and other computational tasks. Future innovations. The advancements in finite automata are expected to drive innovations in various fields, from natural language processing and machine learning to artificial intelligence and cybersecurity.